Hello, everybody. This is Mike Heumann, and welcome to the G2M Research Multi-Vendor Webinar on Advanced NVMe SSDs, Addressing the Blast Radius Problem. We'll give everybody a minute or two to join, and then we'll go ahead and start. All right, thank you again, everybody, for joining. Today, our topic will be Advanced NVMe SSDs, Addressing the Blast Radius Problem. And we have panelists today from Lightbits, Intel, and Kioxia. Joel, you can repronounce that if I did it wrong, because I always usually do. But
no problem.
Sounds good. So webinar agenda, so I'll talk a little bit about the ground rules here for a few minutes. Then each of the vendors will present for 8 to 9 minutes on the topic that they are talking on, their piece of the topic. We'll have 3 key questions for the panel, and during those questions, we'll also have 2 audience surveys, and then we'll do an audience Q&A at the end and a final wrap-up. Just as a reminder, please put all your questions for the Q&A into the Zoom Q&A window. We'll answer those all at the end. And we will also we're making a recording of this, and we'll make the recording and the copy of the slides available to everybody. The links to those will get sent out on Thursday. That usually takes about a day or so for Zoom to process the video. So once that happens, we'll send it out, and everybody who registered will get a link to that. So with that, let's go ahead and get started. So with us are Josh Goldenhar. Josh is VP of Product Marketing at Lightbits Labs. We also have Joel Dedrick, who's VP and GM of Network Storage Software at Kioxia, and John Michael Hance, who's Product Manager of SSDs at Intel, and then finally myself, I'm the manager. So what is the SSD blast radius problem? It's interesting because I think, as we've all known, and maybe I'm sure that John Michael will have more color on this, processors have kind of stopped following Moore's Law, probably did a few years ago, and the growth in the number of devices has slowed. However, on SSDs, we really haven't seen that. You know, if you look at enterprise U.2 SSDs today, 8 terabytes is pretty typical. Max capacities of 16 terabytes are here right now, and 32 is probably just around the corner. And, you know, when you get capacities like that, you know, if you have a 32 terabyte server or a 32 terabyte SSD, it's likely it can support more than a single server. Whereas most servers don't need that much storage. The problem with that is let's say you're sharing it or somehow you're utilizing it across multiple servers. If that one SSD fails, it takes out potentially all of those servers. Conversely, if you were to lose that server that's holding the SSD, perhaps a more likely outcome, then it would make the storage unavailable to the rest of the servers that are utilizing it. You know, adding redundancy certainly is an option. You know, we have RAID 5 and things like that, but that can be expensive. And, you know, the other option is you just keep using lower capacity drives. Obviously, you're not getting the best bang for your buck when you do that. So what our panelists are going to talk about a little bit today is different ways that you can get around this blast radius problem. In other words, how many servers do you take out when your SSD becomes unavailable? And starting with that, we'll start with Josh Goldenhar at Lightbits. Josh, I'm going to pass you control right now. And you should be in control.
Great. Thanks very much, Mike, and good morning, good afternoon, good evening to everybody out there. As Mike just said, I'm the VP of Product Marketing for Lightbits, and we'll jump in to tell you a little bit about what we're talking about. And Lightbits is really about hyperscale storage for all. And what we mean by that is there's lots of us out there that would like to get the efficiencies of the hyperscalers. We'd like to drive down cost. We'd like to take the methods that hyperscalers are using and apply them to our own data centers, to our own scale, to our own private clouds. And that's a challenge because hyperscalers can afford tens of thousands sometimes of developers to work on a very specific task. And moreover, oftentimes hyperscalers have a one program. So if you think about Facebook, for example, in a dramatic oversimplification here, you can think of Facebook as a single application. Now, obviously, underneath the covers, it's made up of many. But the point is that Facebook is completely in control of every piece and every sub-program that makes up the overall Facebook experience, so they can tailor their apps exactly to their hardware or vice versa. But as someone who maybe is part of an enterprise, innovative enterprise, or someone's a cloud provider, you don't necessarily always know what your end users are going to run, or you have lots of different loads. Talking to a financial customer on the East Coast, they said they had over 6,000 legacy applications as they're trying to move into their own private cloud. So building your own private cloud infrastructure, while you'd like to use hyperscale methods, it's a very different environment. And so that's what Lightbits addresses, is providing this hyperscale storage savings efficiency, but it's available to all. So with that, let's look at what's going on today. Very common to have racks full of servers. As Mike was mentioning, they may have a local NVMe SSD in each one for speed. This gives you local flash, which of course is going to perform at the highest levels. It helps you limit your server SKUs because you can fill a rack up with servers that are all the same configuration, as long as you can make use of those drives and whatnot. And the applications themselves usually perform the data replication or data protection. So the drive itself, being DAS, is not protected. And so the application has to do the work. This can cause you problems, though, if you have an application that's not used to doing the work. And then we'll go over to some other issues with that as well. One of the biggest ones is that in this scenario, and Mike kind of pointed it out, let's say especially if you decided you needed a 32 terabyte drive, a drive failure or a server failure necessitates a full rebuild. So if the application is doing replication to keep itself up, like Cassandra, CockroachDB, MongoDB, etc., if a server or a drive fails, you can probably start up a new virtual or container instance on another host, but it's going to copy over the entire contents of that drive. And if it's a 32 terabyte drive, that's a lot to copy over. The other issue is that there's also more than you can eat IOPS. And what I mean by that is these drives, and I believe Kioxia actually here on their drive division has PCIe Gen 4 drives they announced. Hopefully I'm not stealing any thunder there. This is public information. And these drives can just do amazing numbers of IOPS. One drive can do more IOPS oftentimes than a local server needs. So in addition to wanting to share capacity, you actually want to share the IOPS as well. But a problem comes up when you go ahead and try to share this, is that now before you share, the reason you want to share is just what I mentioned here. We find in interviews with our customers that overall on the entire fleet, when they deploy drives this way, they're only getting a 15 to 25% overall capacity utilization. Oftentimes they're only seeing about a 50% performance utilization. That is, if a drive offers 600,000 IOPS, they're hard pressed to use 300,000 IOPS. Capacity literally had a customer say, yeah, we deploy 3.84 terabyte drives in every single compute host. This just happened yesterday. And so, well, how much is used over the entire fleet? He's like, oh, it's barely used. And that's because you just never know, especially if you're a service provider, what customers are going to do. So this is a lot of capacity that has been paid for that's going completely unused. And hence, that expense is wasted. So a lot of folks will say, okay, well, there's an easy solution for this. You should disaggregate. You should take the drives out and put it in top of rack and maybe just use off-the-shelf SPDK or something like that. Just physically disaggregate. And then you can have these servers use the drives over the network. And that way you can use far fewer drives. You could use simple partitioning or namespaces to go ahead and only use the piece you want. Perhaps you could make up a system where you dynamically allocate this on the fly. The problem, though, is what Mike was referring to, is this increases your blast radius, because when I had a single system before, a single drive in a single system, and that drive failed, I only took out that one server. But if I go to a simple top-of-rack solution, that is, I just have done physical disaggregation, and I'm using NVMe over Fabric, for instance, in an open source sense, where I'm literally just making drives available. I call this remote DAS. You have systems that think they have a local drive, they really don't. But if that server at the top of rack now goes away, your blast radius is now effectively the entire rack, or all the systems that were using that one server. So instead of losing one server for a drive failure, depending on how your drives are laid out, you may lose multiple servers. And even if you do RAID protection, in that one chassis, if you lose that server itself, well, then you still lose all the hosts that were using that server. So that really increases the blast radius. Of course, because we're selling a solution, I believe that LightOS is the solution to that. We do what looks like top of rack. However, you can spread your systems over a cluster. And you can have not only a drive failure, which can be taken care of by erasure coding. And to get around the size of the drive issue, of course, we only rebuild in the case of a drive failure exactly what has been allocated. Also, we're thin provisioned. So though your servers or your systems users may see an 8 terabyte volume that's provisioned, they're only using the amount of capacity that they've actually written to. And hence the actual used capacity on any one drive failing may actually be very small. So rebuild is not going to take that long. It's going to be done inside the system versus being over the network, which is another issue when you do DAS. And so hence you can have a drive failure or you can have a server failure and you can keep on going. So your blast radius has been greatly reduced because you're not going to affect a whole bunch of systems in the case of a drive or a server failure. So recovery is going to take seconds to minutes, and it's a lot better solution. This is what it looks like if you're really deploying racks of systems. You can see you'd spread the LightOS cluster over the top, and I see there's been a transformation error from Google Slides to PowerPoint here. So it says NVMe TCP target in the top. But the LightOS servers span racks, and a rack in this case is kind of your failure domain. But you could also have other failure domains per your own definition. You could define it not just by rack, but by row or by power zone, or maybe you have AB power. So we give you a flexible mechanism that's going to fit into your Kubernetes or virtualization environment or bare metal, such that you can define what a blast radius is or your failure domain. You can go ahead and have an entire rack fail and stay up. Or you can have a server in a rack fail, and if you have a cross-sectional bandwidth assigned in your network, you can go ahead and have the drives, the virtual drives that is, still look to be available while a rebuild or replacement happens. So it's a very flexible system, especially specifically architected to take care of a blast radius issue when you go ahead and disaggregate. So in a nutshell, what you get: high performance, you're getting logical volumes that appear and work like local NVMe drives, very, very low latency, high IOPS, high bandwidth. This is going to greatly increase your operational efficiency. So some of the things that Mike talked about is you're going to be able to use that really large drive because you're going to share it amongst multiple hosts. But even though you're having multiple hosts use that one drive effectively, it's virtualized out and protected such that you haven't increased your blast radius. And this all works on standard servers. We're a software-defined solution. Unlike some other solutions based on NVMe or NVMe over Fabric, we do have some rich data services. Thin provisioning, every volume is thin provisioned, so you're only actually using the amount of data that has been written to. And we offer compression with an optional hardware accelerator, so you don't have to use that if you don't want to. It can be 100% software-defined. And of course, more planned for the future. And this is going to greatly reduce your TCO while maximizing your return on investment, the utilization of the devices. And lastly, if you use something like Intel's QLC drives, which are very affordable, they're affordable, but they need you to write to them in basically sequential and large block to get the most endurance out of the drives. So this oftentimes seems to make them suited only for 100% read loads, which of course don't really exist. You have to write to it at some point. And if you don't write to it, quote unquote, properly, that is, if you were to do small 4K writes all the time, you'd greatly impact the endurance. LightOS allows for this, not only allows for it, it encourages it. We have a flash management system that treats the underlying flash drives very, very well by writing to them in large chunks, writing to them sequentially, and this really extends the life of QLC, making it very affordable. So lastly, this lets you disaggregate without increasing your blast radius, and that is that.
Excellent, Josh. Thank you very much. Let's see if I can, if you can give me control, and then we will move on to Joel. Joel is VP and GM of Network Storage Software. Let's see.
Your options, give up remote control. There we go.
There you go. Perfect. Okay, Joel, you should be in control now.
Okay. Do not adjust your set. Control of the vertical. Okay, my name is Joel Niedrich. I'm with Kioxia. I'm GM of Network Storage Solutions, which is the CumoScale business unit. The necessary caveats: CumoScale targets pretty large-scale data centers, maybe 10 to 100,000 compute nodes is our sweet spot or so, and so my comments will apply to that market statement. And of course, this should not be construed as a guarantee about anything that we do or will make. As Josh was kind enough to point out, Kioxia has recently introduced the first PCIe Gen 4 enterprise class solid state disks, the CM6 and CD6. And early in their life, we have rediscovered a number of problems with them. The feedback from customers is they're too big. As has been pointed out, it's a precious few single node application instances that can consume 8 or 16 terabytes. They're too fast. They're north of 1 million IOPS. And again, the number of applications where a single node can consume more than 100,000 IOPS, I'm aware of a couple, but they're extremely rare, other than IO test suites. And they're too expensive. Everyone loves flash in every application. The only consistently reported weakness is it isn't free. These aren't free either, and until they're free, everyone will think they're too expensive. And the final thing is the amount of irreplaceable data you lose when one fails is too large. The blast radius problem. Actually, that's not one of the problems with modern SSDs. That's a fallacy. We'll get to why, but I think you can see that coming. That how much irreplaceable data can you stand to lose? So disaggregating flash. Let's talk about what that means. Scale out flash. The approach is enabled really by the advent of the NVMe over Fabric standard, and high bandwidth networks. Network bandwidth has been growing much faster even than SSD capacity, and so 100 gig Ethernet is routine now. And software like CumoScale and others enables customers to disaggregate, move the SSDs out of the compute nodes, virtualize them into volumes instead of sharing these raw drives, which are too big and too performant, and then share them back over the network to the compute nodes. But now we've made the blast radius really big. If this is a 2U platform with 24 drives in it, now we have a 200 terabyte or 400 terabyte blast radius to deal with. So it seems like we're going in the wrong direction if you actually care about blast radius. But let's talk a bit about what really matters in data protection. And as I've heavily hinted here, blast radius is not one of the things that really matters. The prime directive in storage is don't lose any critical data ever. Every storage purchase decision is a bet your career decision. It's not clear to me, at least, that losing 500 gigabytes of irreplaceable critical data is better than losing 16 terabytes of it. You basically, if it's irreplaceable, you can't lose any of it, even 1 byte. So SSD capacity really doesn't matter and really never has. Losing any amount of critical data is too much. And so when we talk about blast radius, we have to think about what blast radius is the one that matters. Is it the SSD or storage node or rack or power segment or the entire availability zone? What's the one that you care about? The answer is you care about the largest one that could conceivably fail, and your data protection scheme had better span that blast radius, that zone. And so when you're choosing a storage solution, you had better choose one that has the flexibility to provide failure protection across whatever your failure zone, your largest failure zone is. And that needs to be a primary criterion for the choice. The second desideratum for choosing a storage system really, or choosing the data protection mechanism underlying a storage system is don't waste money protecting data that isn't critical, that isn't the primary copy. If you look at the data in use in a data center, actually a relatively small fraction of it is the primary copy. There's a great deal of analytics data, the data lake sort of thing. As SSDs become primary storage, that kind of data is finding its way onto SSDs because they're a cheap enough medium now that you can afford to store basically everything on flash rather than rotating storage. But you don't necessarily need to replicate everything, and so it's important that you replicate the volumes that require it and not replicate those that don't. And that brings up a side point that turns out in practice to be really important. It's not often mentioned, but it's in practice it matters a lot. And that is that something there's a grave shortage of in this market space is people skills. The skills to build and manage a data center of tens of thousands of machines are rare, and they tend to mostly work at Google and Amazon and Microsoft. And so if you're building such an enterprise, you really need to care about the ease of use and the ease of configuration and maintenance of the solution you choose. And so having the capability to span the right failure zone or blast radius, and having the capability to protect only that data that needs to be protected is great, but it needs to be manageable in a way that makes it possible for mere mortals to get it right every time. And that's something that's really a critical thing that I think the Kumascale team is very proud of, the way that we're moving closer and closer to the model of Kubernetes in terms of how we manage storage. We think of ourselves as Kubernetes for volumes. We schedule and distribute and monitor storage volumes in the very same way Kubernetes schedules and distributes and monitors containers and pods. And that paradigm is serving us very well, and it is something that our customers seem to very much appreciate. So in conclusion, a couple of things to worry about when you choose a data protection scheme. First, it needs to span the largest failure domain you have, and SSD boundaries won't be it generally. And protection shouldn't be mandatory. You want to pay only where you need it, as a smaller and smaller fraction of data represents the primary copy, the less and less tenable one-size-fits-all data protection is. And with that, I will turn things back over to Mike.
Thank you very much, Joel. That was a great summary of some of the problems we have in this space, definitely. Okay, and let me now pass it over to John Michael. John Michael is product manager for SSDs at Intel. For anybody who's in the NVMe space, we all know John Michael well. All yours, John Michael, go for it.
Hey, good morning, guys. Yeah, as Mike said, I'm a strategic planner and product manager for our data center SSDs at Intel. It's funny, when Mike asked me to do this webcast, I've been thinking about this problem quite a bit. I actually just recently rewrote our TCO model for QLC SSDs kind of from the bottoms up, and I've been working with some of the top cloud vendors kind of discussing this exact topic. And as the other speakers kind of alluded to, blast radius is kind of a loaded term. It means a different thing to a lot of different people. There wasn't one consistent definition, but for the SSD, I think it's kind of a distraction. And as the other guys mentioned as well, it's like you can't really think about it's one piece to the puzzle. Top cloud vendors and other guys don't talk about blast radius of the SSD. They talk about system durability, availability, total cost of ownership, the things that really matter. So one of the things is, we lived in a hard drive world where hard drives were very large, they had low performance, the failure rates got very bad, especially towards the end of the life of the drive, or if the drives were being misused, in higher temperature thermal environments, or high humidity data centers, for instance. And rebuild times were abysmal. So rebuild times for large capacity HDDs, the nearline or SMR drives, can be in the weeks. So first of all, the move from hard drive to SSD is a huge paradigm shift from people thinking about that problem differently, right? Because losing a large capacity SSD, the SSDs do have lots of bandwidth available to rebuild the storage. So at that point, it doesn't really become an SSD problem. And as everybody noted, it becomes really a system problem with network bandwidth, replication schema, and all these things introducing, being parts of the equation of your durability, availability, and overall system resiliency. So I've given kind of an example here. I think, just to define durability for everybody, it's really how resilient your data is, or, it's 1 minus the probability of data loss annually. Just to illustrate it, like 6 nines durability, so 99.9999, that would mean you have like a kind of 1 in a million chance of losing your data, which sounds pretty good. But if you're at a hyperscale, a VP at Facebook once told me, at scale, probability becomes reality. And that really stuck with me, right? They have to solve these problems for them that are deploying millions of drives in the field. 1 in a million is actually a terrible failure rate. And they're actually going to see many failures at that. So if you're designing a system, if you're a mom and pop shop and you have a single server with a couple SSDs in it, RAID 5 or a standard replication within the box is adequate, and you probably don't care about the probability of a rack or a data center going down. But if you're AWS or they claim 11 nines durability, they have to have resiliency between an entire data center going down, and they actually calculate the probability of like things like earthquakes or natural disasters literally taking out an entire data center. And then you work down the line of the blast radius. If you have an ILR zone go out for a power failure, that might impact your availability, but not your durability. Same thing with the switch going out. It might take a hit to availability or not to durability, but systems can be designed different ways. So part of this is in the new software infrastructure. So their software-defined storage and HCI kind of solve these problems. One of the examples I give is the crush algorithm in Ceph, which is basically doing this. You can kind of identify how where data is placed and make them physically far apart. And there's a long paper from AT&T that basically describes that even just mirroring or two copies of the data is actually pretty adequate for high durability, as long as the data is very far away. The standard in Ceph today is triple replication, and when I heard that, I was kind of appalled. But it's because blast radius is a huge problem with hard drives. They use small capacity hard drives today, like 4, 8, and 10 terabytes, which are not the most cost effective or TCO effective hard drives, but they use them today because of blast radius problems, and then they just triple replicate, which 3x's their cost because the drives are slow. I mean, this is a terrible solution, and you can see with SSDs we have a lot better solutions. And same with VMware vSAN. They have erasure code for like kind of a RAID 5 and RAID 6 for single or dual parity, and they distribute the data across the different servers when you have multiple servers in the HCI. So it's really, the blast radius of the SSD or the size of the SSD. Actually, the capacity of the SSD itself doesn't really mean anything in the overall system. It is, as you would expect, as the drives get bigger, it's more data to rebuild. But as we mentioned, there's a lot of other variables. So I'm going to give an example. As you guys may know, we have a product or software solution called VROC, or our virtual RAID on CPU, which is really our integrated RAID, where we have some functionality built into the CPU that makes it kind of like an integrated HBA. And then we have software, standard Linux software RAID, MD80M, that goes on top of it to provide data protection. And in this RAID 5 solution, we have some custom stuff that we can do, like do a write ahead log to basically prevent against the RAID 5 write hole. But I'm going to describe something that may be a little bit counterintuitive. So, what we're looking at here is this dark blue graph is we're looking at a RAID 5 volume. So 4 terabyte drives in a RAID 5. So you can imagine you have 12 terabytes of storage and 4 terabytes of parity. And this dark blue is the performance of the RAID array. And this is 100% read. This is 70-30 read write. And then this on the right is 100% write. And then, so this is that dark blue, that's performance in IOPS of the RAID 5 array. And then this dark blue is what the performance is during a RAID rebuild. So I'm going to give one example of showing how drastically the RAID rebuild time is affected by all these other variables like network bandwidth. In this case, it's just within the box, so it's really just a function of the performance of the drives, the workload going to the RAID array, and the capability in the drive and the bandwidth. So with no workloads going on whatsoever, this RAID 5 rebuilt in 1 hour and 35 minutes, which was a little bit surprising to me. This 4 terabyte drive, our P4510, which is one of our best-selling NVMe SSDs at Intel, can do 3 gigabytes a second sequential write. So this tells me, if you just did the math, 4 terabytes divided by 3 gigabytes a second, it's about 20 to 23 minutes for rebuild. So this shows me that there's some overhead. I think this was with a 64K RAID stripe. But the number drastically increases depending on what the workload you're running to the RAID array. So if you're running a read workload that about 4x the rebuild time, you're sitting here almost at 6 hours. 70-30 took it above 7 hours, and 100% write workload took it almost to 9 hours rebuild time. So there's huge overhead on the RAID rebuild as a function of what workload you're running. And that makes sense because in a RAID 5, you have to read the parity data, and then you calculate the XOR, and then you write it as you're doing the RAID rebuild. So it would make sense that a overhead would impact the rebuild time significantly. But this is this is just the basic example of 4 drives, but you can see this could be magnified significantly based off what other types of if you have erasure code on a large scale and increases CPU utilization, but you get better durability and you get lower overhead. But these are all trade-offs you use when you're building a system and trying to calculate the durability and availability. So we are going to talk a little bit about it later in the webcast, I believe, with some questions. But what can we do within the SSD to kind of reduce the blast radius? Well, we already said QLC drives are here. Intel sells 16 terabyte QLC drives today. We have a lot bigger on the near horizon, and they offer better TCO and warm storage than many hard drive solutions today. I'm defining warm storage here as your kind of TCO dollar per terabyte per rack, and then kind of a function of IOPS per terabyte. Many hard drive datas are still triple replicated, and with SSDs, you have more IOPS and performance. You can use compression and dedupe. There is many solutions today where QLC offers a better TCO than hard drives. But the first thing is they aren't hard drives. We know how SSDs fail, and they don't fail anything like hard drives. So the first order principle to reduce the blast radius would be to actually reduce the device failure rate. And that's from the SSD side. That's some of the things we're working on. I did just write a blog on nvmeexpress.org on how NVMe SSDs fail and what we can do and all the capabilities in NVMe to help kind of prevent, predict, and monitor those. But most of the reasons why SSDs fail are firmware errors. That's one of the major contributors to, and this is just corner cases or weird states that the SSD can get in transferring data. And many times the SSD is actually in perfect shape. So one of the things we're working on is to have new recovery mechanisms to make the firmware more resilient. So recover from errors. Now in a cloud scenario, they may be completely willing to, refresh and wipe a drive or secure erase a drive in the field to reset it after a firmware fault, rather than sending a technician out to have a failed drive. So you kind of still have the blast radius problem where you're rebuilding the drive, but you don't count that as a failure because now you didn't have to send a technician out there, and it just kind of self-heals. Media errors is something where most common drives today have XOR within the NAND dies or redundancy within the SSD to prevent against media errors. And most modern SSDs can actually have withstand die failures. So this isn't a huge cause, but as you could imagine, when you scale the capacity of the SSDs bigger, then this starts to become an issue, and you have to just monitor it and be able to be more resilient to failures. So overall, one of the things we're doing on the SSD side are, trying to keep improving the SSD reliability. We're already 5 to 10x more reliable than hard drives today. And we think we can push that to maybe 20x with some of these things that I just mentioned. The other thing is when you have a big drive, you really just want to reduce the failure domain. So if you have a 32 terabyte drive, for instance, one of the things we're looking at in NVMe is called zone namespaces. But you can think about this is you have the drive split up into little zones, and a zone can be the size of an erase block, or it can be bigger. And when you have a NAND die failure, instead of just completely bricking a 32 terabyte drive, you could just take it in one zone down, and you could just lose the capacity of that die. So our QLC today is 1 terabyte die, so 128 gigabytes per die, and that's a much more tolerable failure than having the entire drive go down. And NVMe and zone namespaces is a way to actually manage that and be able to actually have a more resilient drive that can withstand errors. So to summarize, we have a lot of interesting stuff going on the SSD from the system side, and my colleagues talked about that quite a bit. There are a ton of different ways to solve this problem. There's probably not really good consensus on what the right answer is, because the right answer is going to be different for every different customer, but we're all thinking about this.
Thank you very much, John Michael. And we'll go to the first panel question. Wait for you to return control. There we go. All right, so our first panel question, and we'll start with Lightbits and Kioxia and then Intel. And the question is, with the blast radius of individual SSDs growing beyond the needs of a single server in many cases, how important do you think networked SSDs, SSD virtualization, or scale-out flash storage software will be to enabling the use of high-capacity SSDs? I know we've covered a lot of that already, but Josh, if you want to throw anything else in that you thought of during the presentations or answer this, go for it.
Thanks, Mike. I think you were right in that, quite frankly, my section covered that our opinion is that the scale-out flash software is going to be the thing that allows you to use SSDs. And that actually is you focused here a lot on high capacity, but we'd like folks to talk about a little bit what Joel had pointed out too on the new drives, is that they have an immense amount of IOPS. So when you're paying basically, or the value of an SSD is in the dollar per IOP, going very, very low, extremely low on these SSDs. You want to share those IOPS. So it's not just sharing capacity, it's sharing IOPS. And we firmly believe that the term SSD virtualization via scale out flash software is the way to go, is go ahead and have a system that allows you to use those drives at the same speeds as if they were local, but virtualizes them out so that you don't have a 1-to-1 ratio of drives. And as far as networked SSDs, I'd add in that I don't see a lot of change there. I know some vendors are talking about just taking an NVMe drive and having it speak NVMe over fabric and just being directly on the network. That doesn't change the fact then that you have you still have a drive out there, and it's still going to be sizable and offer a lot of IOPS, and it can fail.
Very good point. Joel, what do you guys see? I know you guys have looked at networked SSDs as well, so you might have an extra view on that as well, I hope.
We have. I mean, I am not a subscriber to the Christmas tree light, string of Christmas tree lights model of networked flash. I don't think SSDs will sit on a data center network without any intervening software anytime soon. But I do think, at least specifically for service providers, you cannot escape disaggregating flash. You've got maybe a year or two left before you'll be utterly uncompetitive if you're still buying the smallest SSD that Kioxia will sell you, which is not the most cost-effective one, by the way, and mounting one in every one of your compute nodes. You're just going to get killed. You have to share them to be cost-effective, and so it's absolutely critical, business critical for that segment. For the sort of SaaS providers and people that, as the Facebook example, they're running their own code. It's maybe less of a do or die situation, but it's still You know, we have customers, multiple customers who estimate their direct attached flash utilization at 5%, and that's just a situation that nobody's going to tolerate forever. So this sort of software is mission critical for some segments and really important for all of them.
Very good point. I think those are some really good points that you brought up too. I think the disaggregation becoming unavoidable certainly looks the way it's going. You know, John Michael, what do you guys see at Intel on this? I mean, you talked a little bit about it too, but how do you guys see disaggregation going?
Yeah, I don't need to pick sides. You know, we certainly sell SSDs into disaggregated models, and we sell them into enterprise servers, and we sell them into HCI, you know, and software-defined storage. So, you know, they're all different solutions. But, you know, the HCI is certainly, I've seen a lot of development, specifically in stuff like vSAN and VMware, where they're, you know, writing code to be able to take advantage of higher capacity drives. You know, I mentioned in stuff like Ceph and software-defined storage, you know, the use of erasure coding and other compression and dedupe and other replication schema is actually helping the ability to use larger drives and consume them, you know, without having a huge blast radius or overhead. But, you know, as far as networked SSDs, I think I agree. I don't see it in the near term. I think that there's some interesting capabilities long term to have, you know, the SSDs directly attached. But in the short term, I think we need to solve all these other problems with the rest of the ecosystem and standard servers. And the hyperscale guys are going to do this, and they're already doing themselves. So it's more of a function of, you know, what's going to happen in the rest of the industry.
Excellent. Okay, first audience survey question is, to what extent is the SSD blast radius problem an issue for your organization? This is a select one. I'm going to launch the polling. You can just go into your window. You should see something like this on Zoom. When you bring it up, just pick the one you want, and we'll let that run for a couple of minutes while we go to the second audience or the second panel question. And that question is, concepts such as computational storage and smart SSDs are seen as important solutions to the blast radius issue. How useful are these approaches to standard enterprise workloads? We'll start with Joel, and then we'll go to John Michael, and then to Josh. So go ahead, Joel, and take a shot at this.
That's a big topic that's hard to cram down into a minute or two. Computational storage is an interesting idea, but it's not a new one. Computation embedded in memory or embedded in storage has been tried and retried for many decades now. And it typically has the following problem. The cost efficiency of computation in a general purpose processor is about 1,000x worse than the cost efficiency of that same computation in an ASIC. And so you're really, really motivated. If you have something that's you know, computationally intensive, you're really motivated to put it in a fixed pipeline. Putting a general purpose processor, which tend to be power hungry, use a lot of memory, fairly inefficient approach to whatever it is they're doing, if that is fixed function, really doesn't match well with the tremendous cost pressure and power envelope pressure that we feel as a manufacturer of solid state disks. So there are only a few things that you can do productively with data that you don't understand. By not understanding, I mean, when we build an SSD, we don't know what the bits mean that are being stored on that SSD. We don't know which file system they're running. We don't know what the organization of that data is. And so think about, what can you do to data that you don't understand? Well, you can compress it, and you can dedupe it, and you can encrypt it. And I think that's the end of the list. Beyond that, you need to understand the data to add any value to it. And so I think in my view, the future of computational storage, if there is one, will happen when the API of a solid state disk changes to something that gives us more insight into what the data means. And that could be a key value API or some other mechanism for speaking in terms other than blocks and LBAs.
I think those are great points. It kind of reminds me of the days when we did backup at the array level or data protection. And if you didn't know what was going on in the application, the likelihood that you got a consistent data set was pretty low. So I think that's a really good point. John Michael, what do you think on this one?
So I think computational storage is extremely important. So as Joel mentioned, we've had compression, dedupe, encryption. These are stuff that's been built into SSDs before. But I think the really big advantage of computational storage is going to be to specific database queries like accelerating SQL searches in large-scale databases where actually the PCIe bandwidth between the drive and the host becomes a bottleneck, and you really want to really do some of that analytics, down at the drive level. But one, this is not an enterprise thing, and two, I don't think it solves the blast radius issue. One of the things we can look at is just the adoption of stuff like things like NVMe in standard enterprise OEMs servers. It's still in the cloud. We're approaching like 95% or something in 2020 of the SSDs volume sold will be NVMe. In an enterprise servers, it's still about 30%. So they're largely still using SAS and SATA drives and traditional RAID and dash RAID, and HCI is growing, but as you saw, these enterprise servers are really slow to adopt new technologies. So the thought or idea that they would just adopt something new like computational storage is pretty far-fetched to me. But I do see some adoption in the cloud, and certainly very smart people are working on that.
Yeah, I think the other place we've heard a lot about it is probably in the embedded space, where then it's really it's as much putting computation in a small package as it is putting storage next to computation. I kind of agree with that. Josh, what do you think?
I agree with John Michael and Joel on what they said. In fact, I'd almost take it a step further that I think that computational storage might increase the blast radius issue rather than being a solution to it. And what I mean by that is triggered by both folks talking about dedupe has been in drives before. And if you think about what the problem with dedupe is, it's that if you have a server that holds 24 drives and each drive is deduping only its own data, that means that it's far from global. You might get happen to get a high dedupe rate on one drive, but that's doing nothing for the very same data that's on the other drives. And so with computational storage, you get a similar problem in that for that computation to work inside the storage, you have to split your data sets. And then that means you have to have your programming model and everything you're doing consider locality, which is a lot of times what we're trying to get away from in disaggregating storage. If everybody here remembers Hadoop, which seems like only a handful of years ago, was the hottest thing on the face of the planet, that was all about data locality. The data you're working on being local to the server and the drives that it's working on. And now everybody says, that's a horrible model. We have to disaggregate. Okay, so I see computational storage as going the other direction. It introduces data locality down to a drive level and then actually increases the blast radius problem, because now when a drive fails, what do you do about the computation that you were going to do on that set of data? So that's it.
Excellent points. I like that. So I'm going to share it real quick, the results from the first poll here. You should see it there. We will put these into the slides as well. Let's go to the second poll question, your audience survey question. And that question is, when looking at solutions for the blast radius problem, which of these approaches has your organization explored? And you can check all that apply. So I'll go ahead and open up this poll and let people go ahead and answer this one. Okay, and that should be on everybody's screen. Go ahead and take a couple minutes to answer, and then we'll go to the third panel question. And that question is, most of today's solutions to the blast radius issue are external to the SSD. Are there options for new technologies internal to the SSD that can help solve the blast radius issue? John Michael, I know you talked about some of these, but we'll let you go ahead, and then we'll go to Josh, and then finish up with Joel.
Yeah, so I talked a little bit, I know I kind of rushed through, I thought we were going to be kind of short on time, but, making the drive more resilient and more reliable helps the SSD tremendously. One of the things, as you kind of saw, if we know, and we're measuring, how long a RAID takes to rebuild, a 4 terabyte drive, imagine you have a QLC drive that's 30 to 40% slower in write speed and 4 times the capacity. You might be looking at an 8x increase in rebuild time. But that being said, it's still 5x better than a hard drive. So it's definitely a different paradigm. I did mention the things that I'm really excited about, which like zone namespaces, which is not a near-term solution. That is kind of a longer-term solution where you can have the drive fail in smaller parts and actually break up the failure domain. I think a part of that is understanding that, as we talked about this entire webcast, is that most of the time drives are part of a larger storage array, and the data is replicated across different nodes and with different storage use cases. So really understanding all that is really important. But yeah, we are working on this from the SSD side to make them more reliable, and understanding the failure domains and what we can do to help spread that out, and understand that they're going to be used as a collection of drives, not necessarily just a single drive. And that's really important in how you treat this durability problem.
Excellent. Josh, obviously you guys are external to the drive. What do you see as far as this goes?
No, we see that absolutely positively the only way to fix this is to buy some software from a reputable vendor like ourselves. So no. I would only be speculating, more so what's Josh's opinion versus what's Lightbit's opinion. At the end of the day, most of these drives are actually some kind of processor, multi-core processor on the SSD itself. Very often they're running Linux. So anything you can run outside, to some very limited degree, you could run in the drive. So there is possibly extensions to the standard over time. If you actually have software and Linux especially running inside the controller, that the problem is in hardening it. It's kind of what John Michael was talking about, is that the more things you add, the more possibility you have of someone writing something poorly, and that being a firmware lockup. So there's this fight between the functionality you can add to these controllers, but it is possible that the controllers themselves, especially if you think about what I think Joel and I both frown on, which is I like that Christmas tree string of lights analogy for network attached SSDs. However, if you had network attached SSDs and they all had the capability of having an IP address or something along those lines, and NVMe over Fabric as standard for accessing them, you could imagine that it's possible that one drive could be made aware of other drives on that network, and they could talk to each other, and they could do things like erasure coding or replication. And I would definitely want an outside system to be the control plane. So that could happen, but for the most part, I'm going to go back and stick to keep the drives doing what they do best, very, very high performance, being resilient in and of themselves, and have an outside software entity coordinate these to give you the fix to the blast radius.
Excellent. Joel, obviously you guys are doing both software and drives. What do you think?
Well, as John Michael said, we have a lot of people working very hard to improve the reliability and durability of our SSDs. And as an industry, frankly, we're doing a great job at that. But as he pointed out, the largest source of drive failures is firmware lockups. So, if you think about that for a minute, it's not widely known. There was what I think of as a fad a few years ago around building your own SSD controller and software outside of the SSD, doing kind of the open channel idea. And I think part of the fallacy underlying that idea was that this is really pretty easy to make an SSD. You just buy a bunch of these memory chips and you line them all up and read them and write them, and what could be so hard? In fact, the compute power in an enterprise class SSD, not very many years ago, would have been a respectable server. I mean, these things have big compute power, and it's busy, and it's a lot of very complex code. It takes hundreds of engineers to write it, and so thinking that we're going to magically add something to the SSD that we haven't thought of that's going to make the durability so good that we don't have to have external measures external SDS software is I think not very likely. And so for the foreseeable future, I think you know, a solution that that creates durability across a very large failure zone, you know, a building-sized failure zone is going to be required if you care about the data. And if you care about the data, it doesn't matter how, as I said, how little of it you lose. You can't lose any of it ever. And so if it's critical, you have to protect it, and that means it has to be replicated across failure zones.
Excellent. All right, we have 3 questions. I'll start with the first one. The first question is, how much data is non-critical and does not need to be protected? 50%, more or less? Why don't we start with Joel, since you talked last, we'll let you hit it, and then we'll go to Josh, then we'll go to John Michael.
I think actually a large and growing fraction of data is not primary data. So what are the really fast growing sources of bits? Machine learning has to be one of them. Training your ML algorithm to drive your car requires running a very large number of video clips through your GPUs to train the coefficients on the neural networks. But those video clips are stored somewhere in cold storage. I mean, if you lose some of them, you read them out again and keep going. And so performance matters greatly. The ability to source the same data to many compute nodes that are each training a different piece of the network matters greatly. But protecting the data doesn't matter at all. And so you would not want to pay a lot of money to protect that data because you already have another copy of it. And similarly with most work in process data, you know, the intermediate storage, what we've called ephemeral storage, if you're renting it from AWS, needs performance but doesn't need resilience. But then you know, if you need resilience, it better be really good. It's, you know, it's kind of black and white. If you can't lose this data, then you can't lose it. And so to me, it's important that the customer have a easy way, an administratively simple way to identify which is which, and that the storage solution you know, handles the dirty work of protecting the data that needs to be protected, automatically doing the rebuilds when needed, automatically making sure that the data is replicated across failure domains in the proper way, and that you're not, you know, ringing somebody's beeper to get them up in the middle of the night unnecessarily. You just do the right thing. You know, I had many lifetimes ago, I was involved in the computer-aided design software world, and we had a rule of thumb that identifying a problem is worth about 10% as much as fixing it. And that applies here too. You know, identifying that you've got a failed drive is worth about 10% as much as just, you know, find another place to put the data and rebuild the replication and don't wake me up. So, you know, that's
a good point. Josh, what do you think of this one?
Look, I largely agree with Joel. If I get back to the heart of the question, how much is non-critical and does not need protection? I think Joel's examples pointed that out, that's entirely up to the customer on what they're doing. So, you know, back to that AI machine learning example for self-driving cars, the video is eventually going to go, or maybe very quickly, to cold storage, to something very, very cheap and deep. But in other situations, let's take a service provider. A service provider who's providing infrastructure as a service, so you can run whatever you want. They have no idea what the customer's running and what, so they have a guarantee that any data, any storage that's being supplied to the customer, unless it's specifically labeled as ephemeral, is resilient and has high endurance. So therefore, any of that class of storage is going to be deemed 100% of the data has to be protected, even though underneath the covers, you might argue that customer didn't really need that. So it's impossible, I think, for us to say from this side of the aisle how much is critical and how much isn't, because it's really going to depend on the customer's environment.
Yeah, and I think it's a good point in that if you don't know what your data is, then you kind of have to assume that everything's critical. Obviously, knowledge makes it a lot better. John Michael, what do you think?
Yeah, they nailed it. I think the yeah. I mean, so generally, like cloud compute uses ephemeral drives, which are smaller capacity, have really good mixed workload IOPS per terabyte, and they really care about read quality of service in a mixed workload because they're constantly changing the data on the ephemeral drives. Whereas the drives we were talking about, like large capacity QLC, for instance, are mainly being used for storage, and at that point, yeah, the data does need to be replicated and have data protection on it. And I mentioned there are about 1 million ways to do that, but there are different use cases, and they prioritize different attributes to the SSDs.
Excellent. Next question we had is the question is, John Michael mentioned firmware bugs are perhaps the single largest contributor to SSD failures. Is the AFR from firmware bugs related to SSD capacity in any way? And if my SSD was larger by a few of them, does that essentially reduce the blast radius or reduce the failure rate to offset some of the larger blast radius? Why don't we start with you, John Michael?
Yeah. So there's a one way to answer this, I think, is if anybody knows, if you do a RAID 0 of which is just striping across 2 drives, the reliability and annual failure rate of that RAID 0 array is now 2x what the AFR of the single drive is. You basically increased your AFR by a factor of 2 because you have a logical or. If one drive or the other drive fails, you lose all the data. So that would suggest basically having one drive that's twice as reliable is better. Typically in that case. But I think the more interesting thing in this is the question Brendan asked about: do larger drives have higher failure rates? Maybe you guys saw this paper that was going around from NetApp and that was presented at the FAST conference this year. But they released telemetry data on 1.4 million drives that NetApp had used their ONTAP telemetry service to actually get recorded data on those drives. And they found a lot of really interesting stuff about the drives. One, that a lot of customers, weren't using a lot of the endurance of the drives, which was really fascinating to me, but they did see a correlation between higher SSD capacity and higher AFR. I believe that to be a specific vendor issue because there wasn't the sample size of vendors was not large enough, because you can work around, different reliability concerns about, having NAND failures, for instance. But you would imagine if you have more NAND to manage on the SSD, that the firmware becomes more complex and the probability of a firmware error goes up. Now, those firmware issues went down over time as the vendor fixed them. And I suspect we'll see other things in the industry where large capacity SSDs may have, a higher chance of firmware failure at the start, but then they will get more reliable over time.
Excellent. Joel, what do you think on this one?
Well, let me first disqualify myself by saying that I am not an expert on SSD reliability and I'm not involved in SSD design, but having said that, I'll express an opinion anyway. One thing to note here is that that data of the kind that John Michael mentioned tends to be many years old. I mean, it takes a while to accumulate, statistically meaningful failure data. And at the rate that that the technology of solid state disks is advancing, it's, you have to question whether the data matters. I mean, vertical NAND is only a few years old. The NVMe standard is less than 10 years old. And so if we have 5 or 6 year old data on reliability, even of firmware, you have to say, well, does that represent the drives that are being shipped today? And my gut feel is that it does not. I think that when NVMe was relatively new and all of us as drive vendors were trying to figure out how to write firmware that could do, many hundreds of thousands of IOPS, and then, while still staggering under that load, trying to figure out how to deal with a completely new NAND flash technology when we all went to vertical NAND. Probably the very first, paint's not quite dry yet firmware wasn't as reliable as the firmware we're shipping now. And again, I'm not involved in SSD design. That is a total guess, but I do notice that the data suffers from the fact that it tends to be old, and in a fast-moving world like ours, that means it might not represent what's going on now.
Good points. Josh, do you have anything to add on to this one, or are we good?
Nothing useful other than an anecdotal story for you. So, or for everyone out there. When I worked at a different storage company several years ago, we would joke that the largest repair organization on the face of the planet for this was for hard drives or for flash drives is Federal Express. So, and if you don't get that, the issue is that the customer would, of course, say a drive has failed. You'd try to do everything you can to reset it. They would take the drive out of the system. They'd put it in a small box or envelope or whatever, and they'd use FedEx to send in the drive. And of course, we would test the drive, and it was no fault found. FedEx had magically fixed the drive. Now, of course, it wasn't FedEx fixing the drive. It was a reset, a complete power off reset of the drive that reset the firmware, and everything was fine. So I definitely agree that oftentimes is the source of the problem. So, but then, like Joel said, I don't design SSDs for a living, so I can't say if we can fix it. I do appreciate that it's a very tough problem as the functionality expected by drives is increasing, and that means the complexity of the firmware is increasing. And if you squash every bug, at the end of the day, these things are built upon a lot of open source and closed source software, and humans, for the most part, at least for now, are still writing that software. So it's going to be definitely a challenge to fix.
Excellent. One more question. This question is it possible to open compute plus storage resources to upper layer software? If an SSD has 30 terabytes of storage, a 64-core ARM CPU, SSD can let the upper layer software use half the CPU resources and physical layer control half of it. So this is kind of the question along the lines of the open channel discussion we had a little bit earlier. Does anyone want to jump in and try to hit this one?
Yep.
Well, I just just stand back and say, think about an SSD product line that Intel and Kioxia and others compete really hard against each other to be first to market, and to we're battling each other for market share every day on products where getting the firmware done and tested and right is the gating item to getting the drive into production always. And so you're requesting that we significantly complicate that firmware by turning over control of part of the drive to the user for purposes unspecified, which means we need to test that new capability exhaustively while not knowing what you're going to do with it. And you still expect us to warrant the drive against failure, even though you may have abused it. So what's the return to the drive manufacturer for adding this flexibility and thus probably delaying the market entry of the drive significantly? I mean, the reason it doesn't happen is that we're already going as hard as we can go, to compete against each other and to get new drives into market, a month before the other guy. Adding a big degree of complexity because it makes something, convenient for some small fraction of the user base just doesn't really, make the cut in terms of the very complex market requirements that these drives already have to meet. So it's not that we're unaware that it would be maybe interesting. It's just, is some big double-digit fraction of our customer base going to use it for something that makes our drive look better than the equivalent from Intel? That's the bar, basically.
Yeah, I think we saw the same problem with Open Channel, that the number of people that can actually make use of those capabilities on the planet is probably no more than double digits. So, a good point. John Michael, what do you think on this one? Obviously, in subject that you're close to as well.
Yeah, I know we're kind of out of time here, but it's a way to you kind of have answered it with, hey, there are some computational SSDs that allow some of this offload functionality to bigger capacity SSDs. And then there are the more open channel modes, or some of the new models where you're trying to actually place where the data is on the drive, and the host manages some of the flash translation layer and data placement. Yeah, I absolutely think those are going to happen in cloud. Outside of that, I'm a little weary that that's going to happen ever, and it will take a very long time.
Well, thank you again, everybody. Joel, John Michael, and Josh. Really appreciate you guys coming in, and certainly thank you to the audience for being involved. I hope this is good for everybody. And as we said at the beginning, we'll make the recording available in a couple days. Everybody who register will be sent a link to the recording of the webinar, as well as a link to the slides. So again, thank you very much, and have a great day.
Thanks, Mike.
Thanks for the time, guys.
Thanks. Bye-bye.